So, in the next part of this exercise, we have to find where this function is concave up or concave down. We have already figured out the first derivative of this function, and we have seen that it is not defined at 0, so the second derivative will also not be defined at 0, but 0 is still a part of our original domain, so there will be a critical point there. Everywhere else, we can easily figure out the second derivative of the function. You can see that the two intervals, the function differs only by this negative sign, so we only need to figure out the derivative of this part. That will give us e to the negative x squared over 2 times 1 minus x squared, and taking its derivative, we will get negative x times e to the negative x squared over 2 times 1 minus x squared plus e to the negative x squared over 2 times negative 2x. We can factor out negative x times e to the negative x squared over 2, giving us negative x times e to the negative x squared over 2 times 3 minus x squared. So our second derivative function will be g second derivative of x equals, of course, negative x times e to the negative x squared over 2 times 3 minus x squared if x is greater than 0, and of course we have to add the negative sign if x is less than 0, giving us x times e to the negative x squared over 2 times 3 minus x squared if x is less than 0. Now we can see where the critical points are. X, of course, is not 0. E to the negative x squared over 2 is always positive, so it is not 0. So the zeros can only come from this part, which is the same in both cases. So we need to solve 3 minus x squared equals 0, giving us x equals plus or minus square root 3. Of course, our critical points will be like so, with x equals the square root of 3 being in this part, and x equals the negative square root of 3 being in this part. Now, placing our critical points on the number line, we will have the square root of 3 somewhere here, and the negative square root of 3 somewhere here. And creating our table, we will have, of course, these intervals between the critical points, and also a case when it is greater than this critical point, and a case where x is less than this critical point. Now we can write the second derivative of g in our table, and we already know that is not defined at 0 and is 0 at plus or minus the square root of 3. Next, we need to figure out the signs of the second derivative, and we can see that in the x is greater than 0 case, we have a negative sign here. X is of course positive, e to the negative x squared over 2 is positive, so the sign will only depend on this part. Here again we have x which is less than 0, and this factor is the same, so it will be positive. Now to figure out the signs of this factor, we should graph the function, and we can see that this is very similar to our previous derivative, so the graph will look something like this. with its zeros being at the square root of 3 and negative square root of 3. And we can see that it is negative before negative square root of 3, positive between the two zeros, and negative after square root of 3. And now we have everything to fill our table out. Before the negative square root of 3, we must use this function, where we have negative, positive, and negative, giving us positive here. On this next interval, we still use this function, and we have negative, positive, and positive, giving us a minus sign here. On our next interval, we need to use this function because we are above 0, and we have negative, positive, positive, and positive. So we will have negative. And on our last interval, we have negative, positive, positive, and negative, giving us plus sign here. And now we can figure out the concavity of our function g. It will be, of course, concave up on this interval, concave down on this interval, concave down here, and concave up on our last interval. And we are done with the exercise. But we can easily tell that the function has an inflection point here, an inflection point here, and since the concavity doesn't change, it has no inflection point here. And if we were to graph the function, we would find that it looks like this.